This is section 13.1, part B. We're now going to look at the mechanics of evaluating a double integral, and we really need to borrow from what we already know about taking derivatives in a multivariable situation. Just like differentiating, if we're integrating with respect to x, we're going to treat y as a constant, and vice versa. If we're integrating with respect to y, we would like to treat x as a constant. So, we'll take a look at our first example here. I'd like to evaluate this double integral, and then we'll look at what it might mean. We'll start with this. Remember what we said in the last video, that the integral gets evaluated from inside out. So I'm going to start at the inner differential, dx, and I'll do my first integral with respect to x. These limits of integration, the 2 and the 5, are the ones that refer to the x variable. So here we go. This first integral from 0 to 3, I'm just going to save that for later. And then integrating with respect to x, I would get x squared plus 4y is just a constant, and integrating a constant, we'll just get the constant times x, or in other words, 4y times x. Using my fundamental theorem of calculus, I evaluate this from 2 to 5, and those are x values. So to help me keep track, I'm going to write that goes from x equals 2 to x equals 5. And then the dy out here, again, I'm saving that for later. That comes with the second integral. So, evaluating using the usual fundamental theorem of calculus, I'll first plug in x equals 5. So I'll get 5 squared plus 4y times 5. Subtract. Now I'm plugging in the 2. 2 squared plus 4y times 2. And again, that dy is still hanging out there for later. Let's see, that's going to be 25 plus 20y. Minus 4, and distributing the negative, minus 8y. Or the integral of, what is that, 12y plus 21 dy. Now we're ending here with an integral that you know perfectly well how to do. This is just an old Calc 1 integral. If I integrate with respect to y, I'm going to get 6y squared plus 21y, evaluated from 0 to 3. And that's going to give me 6 times 3 squared plus 21 times 3. Subtract. In this particular case, when I plug in 0, it looks like I'm just going to get 0 for both terms. So I have 6 times 9 is 54, plus 63 gives me 117 for the value of that integral. Now, in terms of what that means geometrically, keep in mind this function, the 2x plus 4y, that's the function that determined the height, the top of the surface. I'm not going to try to draw this super accurately because I really can't, but just to give us an idea, if I have this surface, z is equal to 2x plus 4y, that surface is really just a plane, right? Everything's linear, everything's to the first power. So I've got this plane up here as the height function of my surface. I'll draw that in a couple minutes, or at least approximate it. And then the base is defined by this rectangle. X goes from 2 to 5, and y goes from 0 to 3. So let's see here, x, 1, 2, 3, 4, 5, and y, 1, 2, 3. And I'm just going to put in the base here. From 2 to 5 on the x-axis, and I got to kind of imagine a slanted line coming out here. Goes out to 3 on the y-axis. So this is the base of my solid. The height function for the solid is this plane. And again, I'm not going to make an effort to truly draw that one perfectly. I'm just going to kind of generically draw a plane above this. But there'd be some plane up here. And what we just did was we just found the volume with that plane as the top and this rectangle down here as the base. And so that whole thing, that whole solid in there, has a volume of 117. Cubic units, whatever our units are. We won't attempt to draw most of these, but just for this first one, I kind of wanted you to see how the pieces fit together. All right, in example 2, you'll notice that we have the same function, 2x plus 4y. And this time, instead of writing dx dy, I've written dy dx. The inner integral, the first one we're going to evaluate, is the y integral. I also want to ask ourselves to think about, have we changed the limits of integration? Well, you'll notice that the y values go from 0 to 3, which is exactly what they did before. And the x values go from 2 to 5, which is exactly what they did before as well. So because I've not only changed the order of the dy and the dx, but I've also changed the order for the limits of integration, we really are describing the same solid. And we should, therefore, really get the same volume. Let's check it out. Let's try it. So this time, I'd like to go ahead and do the dy integral first. So let's see here. This first integral from 2 to 5, I'm going to leave that out there, save it for later. And then integrating with respect to y, 2x is just a constant. So I'm going to get 2x times the y, plus the integral of 4y, which would be 2y squared. That goes from y equals 0 to y equals 3. And then that dx we're saving for later. All right, plugging in our upper limit of integration, the y equals 3. I have 2x times 3 plus 2 times 3 squared minus, and once again, I'm going to notice that with a y in both terms, when I plug in y equals 0, I do just get 0 there. So I end up with 6x plus 2 times 9, or 18, dx, to do as my second integral. All right, the integral of 6x dx would be 3x squared plus 18x, evaluated from 2 to 5. And let's see, we got to plug in the 5 first. Do a little arithmetic in my head here. 3 times 25 would be 75. Plus 18 times 5 is 90. Subtract. 3 times 4 would be 12, plus 18 times 2 is 36. And that's going to give us 165 minus 48, which gives us back that 117 again. So indeed, it does seem to make sense, and it's logical, right? If we reversed our order of integration and also reversed the limits of integration, we should get the same answer. We're describing the same volume. We'll make that formal on the next page. Here's a little theorem on the order of integration, saying exactly what we just discovered. If I have a continuous function, f of x and y, the value of the double integral over a rectangular region R is independent of the order of integration. That is, I'm going to give you a little notation here. The double integral over the region R, I can just put the region name right there, of f of x and y, dA, that's a little piece of area, defined as either dx times dy or dy times dx, can be written as the integral of f of x and y in the order first dx, then dy, and we'll say x goes from a to b, and y goes from c to d, but it's also equal to the double integral of f of x and y, integrating in the opposite order, dy dx. Y now goes from c to d, so that has to go on the inside integral, and x still has to go from a to b, that now has to go on the outside integral. So again, that's really just nothing more than a bit of notation for you. All right, we will finish up this section in the last video, part C, in just a few moments.